righty. Here we go. Come on, there we go. All right, section 2.4, carbon atoms with formal charge. In the first chapter of this class, we looked at formal charge and how you calculate it for any element. You take the total number of valence electrons, you subtract the number of sticks, then you subtract the number of dots, then you get a formal charge. However, now we're going to just take a look at carbon atoms with formal charges, and especially those in bond line structures. Check it out. It says a carbon, when it's got 4 bonds, it's going to have no charge, right? If you have a carbon, let's say that is bound, you've got 1, 2, 3, 4 bonds like this, it's got a charge of 0. Nothing, nada, okay? No charge on there. However, when a carbon has a positive charge, we have a special name for it. We call that a carbocation. It's going to have a total of 3 bonds, and therefore it's got the +1 charge. And it's also going to have an empty p orbital, and it's going to be sp2 hybridized. Why? Because it will have a steric number of 3. Now, if you were to just look at a bond line structure of this, you would say, well, Mr. Dillon, you're implying that there's a hydrogen here, so this carbon would have no charge. However, if we put a plus next to the carbon in the middle, that implies that there's only 3 bonds to it. And therefore, if we take 4 valence electrons, subtract 3 sticks and 0 dots, we get +1. So that tells us that the carbon has a +1 charge. Therefore, it is a carbocation. Put another way, if you see a positive charge next to a carbon, you can imply that this carbon only has 3 bonds, therefore no hydrogens attached to it, and it is, again, a carbocation. If we have a carbocation on what was formerly a CH2, then you can imply that there's only 1 hydrogen attached to it because we have a positive charge, right? 4 minus 3 sticks and 0 dots gives you +1. And then if we have a carbon at the end with a positive charge, then you can presume or assume that there is 1, 2 hydrogens attached to it. Again, same old rule, 4 valence electrons, subtract 1, 2, 3 sticks, 0 dots, gives us a positive charge. Again, when you see a positive charge, you always assume that there are enough hydrogens to give it a total of 3 bonds to make a carbocation. We can also have what's called a carbanion. You can probably guess that that's an anion. It's a carbon with a negative charge. Well, when we have a carbanion, in that case, we have no empty orbitals. We have an sp3 hybridized carbon, but in this case, instead of 4 bonds, we have 3 bonds in 1 lone pair. Check it out. If we do our formal charge calculation, 4 valence electrons, subtract 3 sticks, subtract 2 dots, gives us -1. And that is why we have a negative charge on our carbon. Hence, it is a carbanion. And so now we've learned how to identify carbocations and carbanions and what they are. Carbanions and carbocations are going to come up a whole heck of a lot in organic chemistry. Going back to that chapter 1, when we were talking about formal charge affects stability and reactivity of molecules. And so you've got to be able to identify formal charges in bond line structures. Very, very important. Where we're getting to is reactivity, but in order for us to understand reactivity, first we have to understand things like dipole moments, formal charges, molecular geometries, hybridization, all that good stuff before we can make crystal meth. All right, the following structure, the structure that's shown down here, is incomplete because it doesn't have any formal charges on it. I'm going to help you out with this one because it's kind of hard for me to walk through this and just say, hey, where are the formal charges? But if I was to ask you about, let's say, this oxygen here, there is a formal charge missing on this. Could anybody tell me what the formal charge on this oxygen highlighted in yellow should be? And you can use the same old formal charge calculation. Yeah, absolutely. Absolutely. It's +1. Yes, thank you very much. Absolutely. Look, if you're wondering, how did the students know it's +1 in that oxygen? Well, they said oxygen has 6 valence electrons. Subtract 3 sticks, subtract 2 dots, which gives you +1. And so the oxygen is +1. if we moved over to this oxygen over here, maybe I'll put a green on it like this. So if I put a green on here, so if I put a green highlighter on the green or on this oxygen, can anybody tell me what the formal charge on this oxygen is? Yeah, exactly. Luke, yeah, Nicole, you're all correct. Absolutely. Both Nicoles are correct. Absolutely. It's -1, right? We do the same calculation. We have 6 valence electrons, subtract 1 stick, subtract 1, 2, 3, 4, 5, 6 dots. 6 minus 1 minus 6 gives you -1. And there's one more formal charge on here. It's on this nitrogen right here. So I'll delete that. Could anybody tell me the formal charge on the nitrogen in green? Probably can do this one a little bit quicker. Yeah, it's +1. Absolutely. We have a plus, where's my pen? +1 charge here. Same rationale as always. Nitrogen has 5 valence electrons, subtract 4 sticks, subtract 0 dots, which gives you +1. Just like that. So very quickly, we were able to look at this interesting ion and determine all the formal charges in this molecule. You know, there's some patterns that you can use to help you identify lone pairs and formal charges. Oxygen has 3 possible bonding patterns. The same 3 are going to come up over and over and over in organic chemistry. Check this out. Oxygen, when it has 7 valence electrons, it's going to have a negative charge. So anytime you see an oxygen with a negative charge, that means it's got 1 bond and 3 lone pairs. You could pencil them in the way I've done right here, or you can just leave it blank. And when you see it like this, it's assumed that it actually has the 3 lone pairs surrounding it. Of course, we've covered the next one a lot. When oxygen has 2 bonds and 2 lone pairs, it's neutral. And in this partially condensed structure here, we didn't even draw in the lone pairs. It's implied that there's a pair of electrons here and here, but again, we didn't even put them in. And then oxygen, as we saw, can have a positive charge. When it's got 3 bonds and 1 lone pair, there we go. It's got a positive charge. And so it's assumed that there's a lone pair on this oxygen here, but we don't even put it in. And we know that we have a positive charge. And so you need to learn all 3 of these bonding patterns for oxygen. I can tell you from experience that all of my students, once they've done enough practice problems, they recognize all 3 of these without any thought whatsoever. If you do all the practice problems, it will be stuck in your head. But remember that oxygen has 6 valence electrons. I would say all students would want to have that memorized at all times. Let's see here, bond line structures. What about nitrogen? Nitrogen is a very common heteroatom in organic chemistry. We'll start in the middle, and we saw that whenever nitrogen has 3 bonds and 1 lone pair, it is neutral. It has no charge. Again, there's no lone pair drawn on the nitrogen here, but it is assumed that there is a lone pair on that nitrogen. Nitrogen can be positive and negative. When it's positive is when it has 4 single bonds and no lone pairs. Again, I'll do the calculation one last time. 5 valence electrons, subtract 4 sticks, subtract 0 dots, gives you +1. So there's nitrogen with a positive charge. And lastly, nitrogen can also have a negative charge. If you have a nitrogen that's got 2 bonds and 2 lone pairs, then you have 5 valence electrons, subtract 2 sticks, subtract 4 dots, which gives you -1. So in this structure here, it's implied that there are 2 lone pairs on the nitrogen. However, you can leave them out if you have the negative charge on there. So now we've covered all the possible bonding patterns for oxygen and all the possible bonding patterns for nitrogen. We've also covered carbanions and carbocations, And with all that in mind, let's try a problem. It says, draw all of the lone pairs on each of the oxygen atoms in these structures. I'm going to redraw E like this, and we have a negative charge like this on the oxygen. How many lone pairs are missing on this oxygen, this blue oxygen? How many lone pairs are missing? Yeah, absolutely. There's 3 lone pairs missing. 1, 2, and 3. Perfect, because it's negative. If it's negative, that means the oxygen must have 1 bond and 3 lone pairs. We go to the next molecule. I'll draw it over here, make it a little bit bigger. What about that oxygen? How many lone pairs is it missing? It's neutral. It has no charge. It's got 2 bonds. Therefore, it must have how many lone pairs? Exactly. Exactly. Yes, yes. 2 bonds, 2 lone pairs. Perfect. And then for the last one, we have what's called an oxonium ion when you have an oxygen with a positive charge. If I just redraw it like this, if the oxygen has a positive charge, it means it's got 3 bonds in 1 lone pair. And there you go. You've done it. Not 2 free electrons. You have 4 total electrons that are not in bonding here, but 2 lone pairs. 2 makes a pair, so 2 pairs, a total of 4 electrons. That's how I'd answer your question, Andrew. I hope that helps. Anyhow, make sure you do all the practice questions where it asks you to identify lone pairs on atoms with charges so that you can solidify your understanding of formal charges. Okay, well, let's move on and talk a little bit about structures in 3 dimensions. We were talking about that in chapter 1. In fact, this morning we were looking at, what was it, dichlorodibromoethane, and we were saying, okay, well, if you rotate the molecule in, such a way. I mean, the thing is that organic molecules, for the most part, are 3-dimensional. They take up 3 dimensions in space. And when we write them down on a piece of paper, or on a screen, we're writing on something that is 2 dimensions. And so we have to find a way to represent a molecule that is 3-dimensional on a 2D piece of paper or a chalkboard or a whiteboard or a screen or whatever. And the way that we do that is using a variety of methods, one of which is a dashed bond or a wedged bond. And dashes and wedges represent nothing more than this. If you have a wedge, so this is called a wedge, what it means is that the bond is coming toward you. It's coming right for us, right? Whereas if you have a dash drawn like this, the dash, you can imagine, means the bond is going away, or is going back from viewer. All these other bonds that are just, drawn as lines, those are all on the plane of the page. But again, the wedge is coming towards you and the dash is going behind you. You can see that on this ring, we have a dash here, and we have a wedge over here. So that means that the OH, the alcohol on the right-hand side, is coming out of the page or out of the screen, and the alcohol on the left is going in the screen or in the page. And then we have a bicyclic compound where you have the bromine on a wedge. It's coming out towards us. You have this CH3, right? This is implied that this is a CH3, even though it's not drawn in a bond line structure, that's going down. And then we also have this thing here. This is called a bridge. And basically, you have the 6-membered ring. So you have the 6 carbons in a ring. And then you have the bridge that's coming up out of the page like this, okay? It's coming up and then it's going back down like that. So it's like you have 1, 2, 3, 4, 5, 6 carbons in the ring, but then you also have a little 1, 2, 3, 4, 5-membered ring attached to it as well. I'll just highlight it here. The 5-membered ring in there. All right. So dashes and wedges. There are other ways to show 3D structures. The the one shown on the far left, this is the Fisher projection. Fisher projections are used only for acyclic compounds. They're usually used for carbohydrates. So carbohydrates, which are covered in organic chemistry too. But what's neat about the Fisher projection is any bond that's horizontal. So horizontal are wedges, even though they're not drawn that way. So this would be coming towards you. 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 And anything that's vertical, so vertical is a dash. So that means anything that's vertical is going backwards. Another one is a Haworth projection or a Haworth projection, depending on your pronunciation. And that one's only used for cyclic compounds. And you can see that you have this alcohol, which is on the opposite side of the ring from the bromine. Obviously, you can see the alcohol is going up and that the bromine is going down. So again, they're on opposite sides of the ring. And then we have this thing here, which is used for a bicyclic compound. I'm not really all that worried about bicyclic compounds today. We might talk about them on Thursday for a minute. Anyhow, there we go. And that brings us to the topic of resonance. So resonance, which is a big deal. Resonance is. And let me just introduce the topic of resonance to you. It's something that you would have seen in General Chemistry 1. And where you would have seen resonance in General Chemistry 1 is when they ask you to draw the carbonate ion. So carbonate is CO3 2 minus. And they say, please draw the carbonate ion. And some students will draw it like this. And then other students will draw it like this. And then 1/3 of the class will probably draw it like this, where they'll have the double bond over here. Did I draw the same thing twice? Sugar. Fix that. There we go. Double bond here. Okay, and then some people will draw this. Okay, and they'll ask you, well, which one of you is right? Which one of these structures is correct? And the answer is that all three of these Lewis structures for the carbonate ion, CO3 2 minus, all three of these are correct. And it's not that the electrons in the pi bond are vibrating between these or something. It's not like they're here and then they move down here and they're here. What it really means is that those two electrons in the pi bond are actually spread out between all three carbon-oxygen bonds. However, there's no way that we can represent that, or it's very difficult to represent that in one structure. And so we use a series of structures that we call resonance structures. And to represent resonance structures, what we do is we put a square bracket around all three of these, and then we put a double-headed arrow in between them, because a double-headed arrow represents resonance. All right, so all it's showing you is that the formal charge is actually more spread out than you can see in one single Lewis structure. Check this structure out here. This is called an allyl carbocation. Very simple structure that can undergo resonance. It says in this case, the pi bond, in this case, the pi bond and the positive are inadequately described by a bond line structure. So this is the allyl carbocation. And this structure, there's nothing wrong with what's drawn here. However, it doesn't give you the full picture of the allyl carbocation, because the positive charge is actually, in reality, delocalized between carbon number 3 and carbon number 1. And if you're saying, like, what? Okay, another thing is that the double bond is actually not localized in between carbons 1 and 2. It's actually shared between carbons 1 and 2 and 2 and 3. If you're going, oh, good gravy, how do you show that? Well, the way that we can show that is based on the fact that all three of those carbons are sp2 hybridized. Okay, if I redraw the allyl carbocation, this carbon is sp2 because it's got a pi bond. This carbon is sp2, and this carbon is sp2 because it's a carbocation. So everything is sp2. That means that each one of those is going to have an unhybridized p orbital. And when all three of those unhybridized p orbitals are touching each other, they overlap. And what that creates is a conduit or a tunnel, as if, that's another way to explain it. A tunnel by which, or where those pi electrons, those two electrons, can be shared between all three of those p orbitals. And we say that those electrons in the pi bond, so pi electrons, we say that they are delocalized. You remember earlier today I said something to you. I said that electrons are like hyperactive children. If they can move, they will. Well, what happens is you have the pi electrons in the pi bond, but you give them all of this room to move. They can move between all three p orbitals. And so how would we represent that? What we do is we represent them with two resonance structures. Now, if you're looking at those and saying, Mr. Dion, those are identical, those are the exact same, all you did was flip it like a pancake, the answer is no, I didn't. If we label this carbon 1, 2, 3, and we label this carbon 1, 2, 3, you can see how the positive charge went from carbon 3 to carbon 1, and the pi bond went from being between carbons 1 and 2 to carbons 2 and 3. And so what we're representing here is what's called resonance. The pi electrons can exist on both sides of carbon 2, so we can have these two different resonance structures. The positive charge can be on carbon 1 or carbon 3, again, so we can draw these two resonance structures. This resonance arrow here, okay, make sure you know that this is a resonance arrow. Sometimes students will try to draw this and say that's a resonance, that's an equilibrium arrow. So resonance arrow, no, it's not. That's not a resonance arrow. That's an equilibrium arrow. And so the resonance arrow in the brackets, what it indicates is that these two structures contribute overall to a hybrid. What's a hybrid car? It's a car that runs on gasoline and electricity, depending on the situation. It's a mixture of two things. And so the overall resonance hybrid is described by both of these structures. Both of these structures contribute to the actual reality, the resonance hybrid structure. Now, if you're wondering, can you draw the hybrid? The answer is yes. However, I never ask my students to draw a resonance hybrid during a quiz or exam. Sometimes I assign the problems where they ask them to do it because it's a good thing to try. However, I never ask students to do it on a quiz. And so the resonance hybrid, instead of showing the pi bond being in one particular spot, they're saying you have a dashed line that shows that those two electrons are shared across all three carbon atoms because all three of them are sp2 hybridized. And then instead of saying you've got a full positive charge on each carbon in each structure, you've got half of the charge here and half of the positive charge here. The structures are not vibrating back and forth. It's not one then the other and one then the other. The analogy that we use is a nectarine. If you've ever had a nectarine, they're freaking delicious. But what is a nectarine? A nectarine is in fact a hybrid of a peach and a plum. You don't look at a nectarine 1 minute and it's a peach, and then look at it another minute, it's a plum. It's always a nectarine. It has the smooth skin on the outside like a plum, but it has kind of the insides of a peach. Okay? The nectarine is a hybrid of the two, the same way that these two resonance structures describe the overall resonance hybrid. Another example would be a mule or a burro. If you cross a donkey and a horse, you get a mule or a burro, which cannot reproduce. You don't look at a mule and 1 minute it's a horse and 1 minute it's a donkey. It's just a mule. But it is a mixture or a hybrid of those two things. And that's what a resonance structure is. And so why does resonance occur? Because those delocalized electrons that are like hyperactive children, the more spread out that they are, lower energy and the more stable they become. And so resonance serves to stabilize a molecule. Those electrons, instead of being confined to one spot, they span a greater distance, giving them more freedom. Everybody likes freedom. Well, at least I do. Anyway, so if you give the electrons more freedom, it stabilizes them. The charge is spread out over more than one atom, and therefore the partial charge, which exists instead of a full charge, is more stable than a partial charge. Well, that covers an introduction to resonance. And so what I would recommend doing before our next meeting is reading the rest of the chapter and trying as many practice problems from chapter 2 as you possibly can, because next class, we're going to begin the topic of curved arrows, by which we can actually represent the flow of electrons to go from one resonance structure to another.